Hello, welcome to the webinar today. My name is Jay Schultz,
And I'm Tom Hickey.
and together we are going to present how to leverage the best of hydraulics with emerging battery electric technology for mobile equipment. We hope you enjoy it. So today we're going to talk about a quick introduction to the whole scenario that we lay out. We're going to go over the application that we've picked out to discuss and migrate into electrification, and then identify the possible system architectures that you might want to go over or use when you're making an electric equipment, and review the steps and considerations when you are electrifying any platform, so we can arm you with some good knowledge. And then finally, some assistance to help you with specification and selecting some components. So we hope you enjoy it today. So let's lay out a first scenario. Let's pretend for a moment that you're a manufacturer of tractors. And while this is the scenario we pick out, the principles that we're going to be discussing here are relevant for any type of mobile equipment. So we're going to go over the key hydraulic functions right now that make up this internal combustion engine powered tractor. And so the first one is the propulsion system, and typically that is a hydrostatic transmission. Connected to that is a tandem gear pump, one gear pump for steering, and the second gear pump for the implement system, which would control the bucket tilt, the bucket lift, the hitch, as well as the auxiliary hydraulic power system that could be exported to some type of tow-behind device. So this typically is makes up the whole demand for the hydraulic functions for the most part, not in its entirety, but these are the major power usage systems. So before we go any further, let's just really quickly discuss the strengths and weaknesses of hydraulics. So the first of all, a couple of strengths are it's very simple. The technology is very well known. Power distribution is very efficient and very easy. And when I say efficient, it's very easy to spread out that power among different parts of the vehicle or the machine using pumps, valves, etc. The power, or rather the torque density, is very, very good, and you can deliver a tremendous amount of torque in a very small package size. Shock and dampening is very well known and very great and excellent for shock absorption. So on these heavy pieces of equipment, it's a technology well suited for that. And component costs, certainly hydraulics is ubiquitous, high volume, mature, and it lends itself very effectively to being very cost effective. The weakness is, of course, efficiency. First of all, simply because internal combustion engines are very inefficient in and of themselves, and typically the way the hydraulic systems are architected currently with the internal combustion engines can further add to reduced efficiency. Leak points, obviously, with fluids and hoses and lots of components, there's possibilities for leaking throughout the vehicle. Maintenance, of course, with hydraulics is well known. Oil and filter changes, leaking components, as I mentioned, all create added costs. And finally, internal combustion engines have a lot of noise, and noise on electric vehicles and electric machine is bad. And so hydraulics tend to also have significant noise, but has often been secondary to the internal combustion engine. So together, those two systems make up a lot of noise that are certainly drawbacks. So a couple of quick drivers why making the change is important. First of all, sustainability. We all care about the environment that we live in, and we want to leave it in a better place for our generations to come. Regional regulations are also part of the trend to migrate to electrification, and so to be able to sell pieces of equipment and machinery into certain markets, we need to comply with those kinds of regulations. Believe it or not, electric vehicles and electric machines do have a lower total cost of ownership. And so it's a hidden cost. It's a upfront cost is higher, but over the long term can be cost effective in that sense. Improved responsiveness and productivity is also a feature due to some of the characteristics of the electrified systems can actually improve the responsiveness and get more work done out of the machines. and clearly lower greenhouse gases as we remove or reduce the internal combustion engine. Clearly, there's no more greenhouse gases that are emitted into the environment. And then, as I mentioned in the last slide, noise is a big issue. So the more electric systems that you have on these vehicles, the quieter it's going to be. Certainly, once you remove the internal combustion engine, it's significantly quieter. And then virtually maintenance free on the electrical side, that is. The hydraulic side still are going to have your typical maintenance associated with it. However, the electrical side is very much a maintenance free system. And so I'm now going to turn it over to Tom to discuss some of the redesigns.
Thanks, Jay. So essentially, kind of when you're first looking at your existing system and what to consider as you're moving forward, your first is getting a nice list of all the different individual functions of what your machine's doing. What are you actually trying to achieve with this machine? And then what do all of those functions require from a power and a torque standpoint at their maximum worst case scenario? And then on the second side of things is what's the duty cycle look like over that time period? So certainly some of those functions are going to be able to, are going to require at some point a high amount of power, but as you average that power demand over the course of the duty cycle, it's going to be something lower than that. And so you want to consider that as well as you're starting to kind of figure out what size battery you're going. In this case, we've broken it down into 3 different scenarios, and the first being extreme scenarios, and the first one being the driving at full speed with an attachment running. And so in this case, we're going to assume that a propel function is demanding the full 18 kilowatt hours at full speed, full load, while steering, which would be demanding 1 kilowatt, and then while sending 6 kilowatts to the back of the tractor to that auxiliary attachment that's either mowing or sweeping or doing something. That total is going to require 25 kilowatts. The second scenario, which is probably the more common scenario, is just driving that tractor around. And so in this case, we're going to assume it's going at full speed, which demands that full 18 kilowatt hours. But you'll see that we're not really demanding any other power for any of the other functions. And then the last one would be the lifting a full load of dirt while moving at half speed. And so this is more of like that kind of implement running where you're messing with a load of dirt, you're scooping it out, putting it to another location. And so that's going to require a little bit of propel. It's going to be a heavier tractor, but you're not going to be running as fast as speeds. You're still going to be steering, and then you're going to be using those implement functions a lot, which are going to just be demanding a lot of power intermittently. In this case, 8 kilowatts for the bucking, lifting, and lowering, and then the tilting function is going to require 7 kilowatts. Notice that we're not running anything on the auxiliary, and the hitches are that's only going to be used for connecting things, so that's also not really going to be in demand. So after you look at all 3 of these scenarios, you notice conveniently that the total power is 25 kilowatts of demand that might happen at any moment from the operator. But the thing is that that's not what the operator is going to be demanding over the course of the entire duty cycle. They're also going to be demanding somewhere in between that 0 and 25 kilowatt power demand over the course of the work. So in this case, we have an operator spending 3 hours in a day, very conveniently spending the first hour doing that first scenario, which is just running the attachment. The second hour is going to be riding that tractor around. And then the last hour is going to be spent moving dirt. And obviously, maybe there's someone out there that uses the tractor exactly this way, but just for the purposes of presentation, this is going to be how we're kind of laying it out today. So on that first thing in the running attachment, you notice how I said at the worst case scenario, we're going to be demanding 18 kilowatts of power to that propel. But we're not running, the operator isn't running that tractor at full speed over the course of that entire hour. In fact, they're probably running more often something closer to half of that speed if you average it all out together. And so in this case, we add it all up and we say, okay, 8 kilowatt hours of energy required to run that propel function for that first hour. The other thing to note is that we're also running the auxiliary power. Now this one's a lot more consistent. You're kicking on your auxiliary power, you're sending flow back to your tool that you're hooking up to, and that's just going to demand 6 kilowatts continuously over the course of that hour. So in this case, we consumed 6 kilowatt hours of energy. In scenario 2, now we're just riding, and it's the same kind of scenario as that first one where we're just kind of driving the tractor, we're steering intermittently, and so in this case we assume it's 3 kilowatt hours of energy pull. And then the last one's going to be the moving dirt, which is a lot more intermittent functions here. You can see there's a lot of up and down mounds there for that bucket lift and bucket tilt functions, which was on the course of somewhere 8 kilowatts, 7 kilowatts for each function. But after you average that over the course of that hour, it's down to 5 and 3. So after you kind of run this analysis for each different function, for each scenario within that duty cycle, you can add up the total energy usage, which in this case we determined to be 29.3 kilowatt hours over that 3-hour time span. So 29.3 kilowatt hours with a 25 kilowatt pole. Now we're getting, even closer to what our battery requirements, our power and our energy requirements are going to need to be to effectively run this machine for its desired duty cycle. However, that's 29.3 kilowatt hours of actual useful work. And what our machine is actually going to require from an energy standpoint is going to be significantly more than that, because of the efficiencies that you got to factor in of all those components that are transferring that power. So in the case of an internal combustion engine system, 29.3 kilowatt hours of useful energy that's being applied, but you're actually pulling 132.57 kilowatt hours of actual fuel to be able to do that. And it's kind of weird to talk about fuel in terms of kilowatt hours. I think we're more used to gallons. And so to put things in perspective, that's about 4 gallons of diesel, I believe, is the conversion we did for this 132.57 kilowatt hours of use. So significantly inefficient. Right here, this very much illustrates kind of the challenge around or the benefits of moving away from internal combustion engine technology towards an electrified system. So the next architecture we're going to look at is now just simply taking out that internal combustion engine and replacing it with an electric motor and a battery. And so right off the bat, you'll notice the efficiencies have improved significantly. We're saying 97% at the inverter and 96% at the motor. So after factoring in those efficiency gains right there, the battery size, rather than 132 kilowatt hour battery, which is massive, we're able to go and look at something closer to 42.71 kilowatt hours. That's something that would be a little bit more in line with being able to do this 3-hour duty cycle that we drew up here. However, there's still ways to improve this system. And so another option to look at is to kind of, what are the functions that are going to require the most power? What are the functions that are going to be least efficient? And just find ways to improve the efficiency of our total system. And we're going to start with the most demanding function, which is the propel function. And right now that's being done by hydrostatic transmission, which we estimated to be at 88% efficiency between volumetric and mechanical efficiencies. So the first change we're going to do to our system is to take that hydrostatic pump and replace it with an electric motor as well. And so now we have a 2-motor system, but now a much more efficient propel system. And so we're going to be able to save 2.13 kilowatt hours of battery size to achieve the same 29.3 kilowatt hour of output. So the next observation we're going to make is to notice that these 2 implement pumps are still together, they're tied together. So when you need one, the other one's still going to be spinning as well. And so what this what results in is power demand and power draw and energy consumption that otherwise isn't incredibly necessary. So the next thing we're going to do is look at breaking up these 2 pumps or these 2 systems so that they can work more independently of each other. And so to do that, add another electric motor. And so we have one dedicated electric motor specifically to steering. And so this system opens up the opportunity to just steering on demand, while then the other motor, which is going to be handling a little bit higher torques, that's going to be set up to run your attachment power, your implement bucket controls, and then the hitch function as well. And so right there, you notice a pretty significant savings in efficiency, and we're able to reduce our battery size by another 4.02 kilowatt hours. But there's more that can be done as well. And so the next observation is you're looking and you're seeing, okay, that's 75% efficiency of the implement functions. There are, out of that pump, there's certainly room for improvement there as well. So what if we take that and get rid of the hydraulics as much as possible, basically make it all electromechanical actuators? And so this is now the option 4, which we have electromechanical actuators to run the bucket tilt functions, the bucket lift lower functions, as well as the hitch. And so this results in 5 separate independent electromechanical actuators. And as a result, this again saves more energy requirements to run the same functions. In this case, we cut it down to 2.77 kilowatt hours. Now, if anyone's familiar with electromechanical linear actuator technology today, you'll know that it's complex. There's concerns around handling shock loads. And lastly, it comes at a pretty hefty premium. And so right off the bat, you're looking at this system. This is probably a very massively expensive system, and it's not viable to enter the market in this current state the way it is, with the technology being what it is today. And so are there any other ways to improve the efficiency of this tractor outside of electromechanical actuators? And well, the answer is, of course, yeah, there are more efficient pumps than that 75% efficient gear pump. We could look at a variable displacement pump that allows you to change your flow on the fly and demand only the flows that you need. We can also put, in this case, we put a bin axis pump, which is a lot more efficient as well. And right off the bat there, that's also going to be able to save you, in this case, we calculated to be through 3.7 kilowatt hours of energy. And so this just gives you kind of an idea of some of the thought process of what options, there are to be kind of considered. And so, after you had a chance to look at all the options, then it's good to kind of lay them all out and understand some of the pros and cons of each. And so, in this case, there isn't really one right answer, but we're looking at it from a perfect balance between cost and efficiency. Option 3A seems to be the most attractive option because it only uses the 3 motors, 2 hydraulic circuits. You're still going to get the functionality you need, and it's also the most efficient option as well. So I'll hand it back off to Jay to take off.
Thanks, Tom. So now one thing to think about too, as you kind of consider the various architectures that would be right for your machine, is to consider like what components are going to be needed. And so it would be good to consider a supplier that can help with all of these various electrification technologies, from the existing hydraulics and re-architecting those hydraulics all the way up through all of the electrical systems. And so, there's a lot of considerations that we're going to need to be familiar with. For example, you need to understand very fluently the hydraulic system pressure and flow, and how to translate that back to what might be the best electric technology for that hydraulic system, and how that fits into motor torques and speeds and things like that. As well as the current draw, because not all motors and not all electrification technology has the same current draw. So from that perspective, how are you going to right size all your cables and understand what you're going to need all the way back up to the battery pack from a voltage and the supply of amp hours available at that size. So, and the final thing might be mounting and size constraints. What are the dimensions that you have for the electric system? Because a lot of electrification technology comes in different shapes and sizes and can do essentially the same amount of work. So having a supplier that is fluent essentially in the languages of the hydraulics and the electrification technologies is a very important consideration. So we hope that Parker Hannifin could be a source for you for everything on your electrified vehicle. Some of the other considerations here to think about is things that we didn't really talk about in this webinar, was to address the valving and any components downstream of the pump. Really, we didn't discuss that. If there's a lot of efficiencies that can be gained by understanding that system complexity and how to reduce the complexity there, because with electrification technologies, there's a lot that can be done and re-architected in the hydraulic side to save valving and to save percentage points here and there. Another area to address is the control strategy and how all of these components will respond to the operator command. So is it a joystick control system? And how are those signals being sent to the hydraulics and the electrified system? What's your control architecture? And so at Parker Hannifin, we also have a complete portfolio of machine and vehicle control systems, as well as IoT technology to push that control up to the cloud for access anywhere. And then ultimately, the specific platforms and application needs will help dictate what the overall system will look like. And so really a open conversation between engineers at the vendor or the hydraulic and electrification supplier, as well as the engineers at your facility, to really understand what the application needs to do, and that can help drive the answers to the best components possible. So to recap here, when we go through a system redesign process, we want to define the individual functions and know what those are. Calculate the amount of power required for each of those, the maximum power that you might see at any given time, as Tom spoke about earlier. And then furthermore, to figure out the duty cycle. Again, in this scenario, or in the internal combustion scenario, wasn't that important because you have essentially a massive amount of energy in your fuel tank. So analyzing the duty cycle is not that important in internal combustion engine vehicles, but when you're using battery electric technology, it is very, very important, and to understand how much useful work you need in a typical day and how much energy that will require. Review the possible system architectures and consider all the pros and cons. As Tom went over a number of different architectures between the cost of the electrification system and the performance and efficiencies. These are all things that we can discuss and help define with you to consider the business case for you and the customers, and then also arriving at the most efficient technology or architecture given the various constraints that you might have. And then finally, sizing and speccing the components specifically that will fit the required design. And so that's something that the vendor, the manufacturer of this stuff can really help you define and arrive at a part number, and then give you some quotes for that. And at Parker Hannifin, we have developed a really concise system sizing tool, or an estimation tool, where you are able to download it. Just scan this barcode, because there's no links here, so take your phone and scan it. It'll bring you to a website, and you can just download this Excel file, which will help you estimate all of the functions that you have, what the power is, whether it's on or off, and some of the duty cycles. A lot of the same stuff that we looked at in the examples here today were estimated on this tool. So I encourage you to download that. And certainly, if you have any questions at all, please reach out to myself, Jay Schultz, or Tom Hickey here at Parker Hannifin, and we would be happy to help you out in any way we can. Thank you very much for your attention today, and feel free to get in touch with us. Thank you.